So, good evening, ladies and gentlemen. Welcome to the annual Math Science Senior Symposium. Today we gather to observe and also celebrate the remarkable achievements that our seniors have done. They've dedicated countless hours, sleepless nights, preparing these presentations. Each year, the symposium serves as a platform for their young minds to not only be tested, but also to shine. We won't take questions in between each of the talks for time purposes, but after all the presentations, you should go out and look at their posters, but you should also go up to them, congratulate them, and talk with them if you have questions about their presentations that you hear tonight. Well, that's all I'm going to say, and I hope you guys enjoy.
Hello everyone, my name is Natasha Helfrett-Kennedy and my project measured the association between concussion history and perceived psychological distress in a sample of Alabama high school football athletes. To begin this study, the first thing I looked at were the risks and benefits associated with sports participation. In the participation of high contact sports, there's a higher probability of sustaining a brain injury due to the physical impact. In one study across 20 high schools, the average concussion rate for all high school sports was 4.7 out of every 10,000 athletic exposures. That same rate for football was 10.4 out of 10,000 athletic exposures. Despite these risks, there are obviously numerous psychological benefits to sports participation, especially as an adolescent. This increases the need for studies focused on adolescent youth participating in these high contact sports in order to better understand how their mental health is impacted by sustaining brain injuries. Now, the most common brain injury from football is something we all can probably guess, a concussion. The sudden movements that lead to a concussion can stretch and damage brain tissue, triggering harmful changes in the brain that can lead to both short and long-term effects. Some of the most dangerous diseases that may arise from sustaining multiple concussions are chronic traumatic encephalopathy, or CTE, and second hit syndrome. CTE is a neurodegenerative disease caused by buildups of a protein called tau in the brain. These buildups can only be seen through an autopsy, and therefore CTE can only be definitively diagnosed post-mortem. Second hit syndrome occurs when an individual sustains a second head injury prior to full recovery from an initial one. Athletes who sustain a concussion and return to the sport too soon appear to be at a higher risk for developing second hit syndrome. Despite these more physical impacts, concussions have also been associated with numerous mental health issues, such as increased psychiatric hospitalization and self-harm in children, and increased impulsivity and aggression in former collegiate athletes. In addition, symptom resolution time has also been positively correlated with increased anxiety levels in children. The mental health component that I looked at was psychological distress. Psychological distress is a state of emotional suffering characterized by symptoms of depression and anxiety. But now, with all of this kind of background information in mind, what makes this particular study so important? To begin, current research has largely been limited to collegiate athletes or white athletes with accessible healthcare or private insurance. However, there is differences in how different athletes respond to a concussion. This especially is dependent upon the area that they live in and the socioeconomic factors limiting them. One study found that sports-related concussion outcomes and experiences vary across these different demographics, and this shows discrepancies in post-concussion recovery timelines and means we cannot generalize the previous research to this demographic. In addition, as I sort of mentioned before, all these athletes were in attendance of Title I schools. Therefore, many of them are living in communities where a large number of families are living at or below the poverty level, indicating that numerous of these athletes may be dependent upon football scholarship in order to finance their collegiate education. Thus, after an injury, athletes are more incentivized to return to play sooner rather than later in order to not lose viable playtime. In addition to this, another study found a higher proportion of Black athletes that did not report a concussion or bell ringer sustained from practice or games than white athletes. This highlights and increases the risk of returning to play too soon, playing with concussion symptoms, or a concussion going undiagnosed, which can lead to persistent concussion symptoms, increased symptom severity, or worst case scenario, second hit syndrome. Lastly, the demographics of collegiate and professional football has been shifting to overrepresentation of Black athletes, as the US population of Black people is only 13.6%, yet they represent nearly 50% of Division I and Division II collegiate athletes. In addition to this, the NFL has also been experiencing this shift. As you can see by these purple lines here, this represents the number of Black athletes from 1980 to 2020, and it's very clear that upward trend. So with all this information in mind, the objective of my study was to determine the association between concussion history and perceived psychological distress. To do so, my lab and I utilized the Promise Psychological Stress Experience, or PSE measure. We obtained our survey responses by iPad-administered surveys to our 262 participants. In addition to them answering numerous different surveys using different measures from both NIH Toolbox and Promise, we also obtained demographic information and medical history, including both undiagnosed and diagnosed concussion. Due to the overall severe underreporting of concussions and the socioeconomic factors limiting the participants of this study in obtaining a diagnosis, undiagnosed and diagnosed concussion history was combined into one. The mean age of the sample was about 15 with a margin of error of 1. The school type and school year were approximately evenly distributed among year and urban or rural school status. Race is heavily skewed as over 50%, or of over 95%, of the sample identified as Black or African American, and the average PSE score of both the sample overall and those with no concussion history is about equal at 15 to 16 with a margin of error of 7. However, the average PSE score for those with a concussion history was significantly higher at around 18 with a margin of error of 8. Chi-square analysis was performed for age, school type, year, and race and concussion history. No statistically significant difference was found for all except for race. However, out of our 4 white participants, 3 had sustained a concussion. Therefore, this result is simply due to the uneven sample sizes and is just a type 1 error in our analysis. Based off the results of a Kolmogorov-Smirnov test for normality and visual inspection of the PSE raw score distribution graph, we knew that the data was skewed, and therefore we had to use non-parametric means in order to analyze the data. So we used a Mann-Whitney U-test, and that yielded a p-value of 0.019. From that, I was able to conclude that there is a statistically significant difference in the PSE scores of those with a concussion history and those without, indicating a positive association between concussion history and perceived psychological distress. As previously discussed, there are important psychological benefits to sports participation. The average PSE score of this sample is relatively low, indicating that athletes are reaping these health benefits. However, nearly 20% of our sample had a concussion history, and their average PSE score was significantly higher. All participants of this study were adolescents, and as adolescents, their brains are still developing, yet can experience adverse effects due to the traumatic brain injury itself, as well as these increased levels of psychological distress they are experiencing, and the other associations that have already been made between stress and other mental health factors. The future brain health of these athletes is reliant upon adequate support systems and response time to their injury. But because all of these athletes are in attendance of Title I schools, many do not have access to appropriate health care, or their schools do not provide them with athletic trainers. Concussions overall are a very highly treatable injury, and rapid diagnosis and treatment may reduce their mental health impacts. However, this requires that access to health care that many Black Alabama Title I athletes simply do not have. In future research, I would like to isolate the positions of the athletes. I'd also like to perform the same study or something similar among different high-impact sports, and to emphasize this point of generalizability, I would also like to include women in the sample. I'd like to give huge acknowledgments to the following people here, and there are my references. Thank you all for listening.
Hello, can you hear me? Okay. All right. Good evening, everyone. My name is Rishi Raju, and my project is titled Identification of Doxorubicin Treatable Cancer Gene Mutations Through Quantitative High-Throughput Cell Proliferation of Yeast. I know that's a mouthful, but essentially my project explores a novel approach to cancer treatment using yeast to model human cancer growth. And before we start, I'd like to acknowledge the following people who helped me along the way. And yeah, let's get started with the problem. The effectiveness of cancer chemotherapy varies based on the genetic makeup of the patient. So in order to better treat these patients, we desire some sort of prognostic marker in their genes that tells us if chemotherapy is predicted to be effective in treating them. So based on their genetic makeup, how can we predict which patients are more likely to respond positively to chemotherapy? That is the question I sought to answer. So how can we do that? We can use yeast. So of the 6,000 genes in the yeast genome, roughly 2,000 of them have corresponding evolutionarily conserved human ortholog genes that regulate evolutionarily conserved pathways in humans. And we leverage this evolutionary relationship between yeast and humans to make predictions about human chemotherapy outcomes using what we observe in yeast. And to do that, we use something called quantitative high throughput cell proliferation, which is abbreviated as QHCCP. And what that entails is for each of the 6,000 genes in the yeast genome, we knock the gene out, perturb the yeast culture with some concentration of the chemotherapy drug, then quantify that gene's influence on yeast chemotherapy susceptibility by comparing the growth of that knockout yeast culture to a parental control yeast culture in which no genes were knocked out. And to account for something called the Warburg effect, which says that cancerous cells prefer glycolysis over respiration, we do this test in a respiratory medium and a glycolytic medium and then compare the two to eliminate any confounding. And the drug we chose to analyze is called doxorubicin. It's a common chemotherapy drug. It's used to treat breast cancer, ovarian cancer, and lung cancer. And we determined for each of the 6,000 yeast genes which enhance doxorubicin susceptibility and which suppress it. And this is just a simplified model of what QHCCP does. I said yeast has 6,000 genes. Let's just look at two, genes A and B. Let's say we have a yeast culture that has both genes A and B active. We apply the doxorubicin treatment and we establish some baseline level of cells that get killed. And then now let's knock out gene A here in the middle, and we apply the same doxorubicin treatment, and now there's increased killing. Well, what does that say about gene A? It means that gene A is a deletion enhancer of doxorubicin cytotoxicity because more cells have died. Conversely, let's say we knock out gene B, and now there's decreased killing when we apply doxorubicin. What does that say about gene B? It means that gene B has suppressed the susceptibility to doxorubicin. So after we make our observations in yeast and determine which genes significantly alter yeast doxorubicin susceptibility, we can assume that the same thing happens with those 2,000 corresponding human ortholog genes when we apply the chemotherapy drug to human cancer patients. And combining the predictions of our yeast model with real cancer patient data, we have this quantitative method to predict which cancer patients are more likely to respond positively to chemotherapy. So how do we do that? Well, we took the 6,000 genes of the yeast genome, we used QHCCP, and we found 225 yeast genes that significantly altered the yeast susceptibility to doxorubicin. And then we used a tool called DIOPT, which is an ortholog prediction tool, to get the 225 corresponding human ortholog genes to those 225 yeast genes. We took those human genes, we put them into a database called UALCAN, which is a cancer genomics database, and that tells us for each of the genes, are they under or overexpressed in cancer patients? And also, do those genes significantly alter a cancer patient's survival? We take the output of that database and we apply our yeast observation model, and that gives us a list of therapeutically relevant human genes, which is what we want. So we have our yeast data. How do we actually integrate it with the real patient data? Well, I mentioned before that we have the over and under expression data, and what we want is for the genes that enhance doxorubicin cytotoxicity, we want those to be underexpressed, and for the genes that suppress doxorubicin cytotoxicity, we want those to be overexpressed, because then the tumor is predicted to be more susceptible to doxorubicin, and thus doxorubicin chemotherapy will be more effective in treating the cancer patient. So if we look over here at this plot, this is just, I chose this gene arbitrarily, it's MCTS1, and this plot shows patient survival over time. The blue curve represents patients with underexpression of that gene, and the red curve represents patients with overexpression of that gene. And in this particular plot, the blue curve is over the red curve. What does that mean? It means patients with underexpression of that gene exhibited increased survival, and the p-value is less than 0.05. So that means this gene not only has significant over and underexpression values, it also has significant survival altering capabilities. So we did that with the 225 yeast genes, and we found across 3 types of cancer, breast cancer, ovarian cancer, and lung cancer, we found 166 genes that, if mutated in cancer patients, will increase the cancer patient survival when we give them doxorubicin chemotherapy. And those genes are in the middle column here. And over here in the rightmost column, we further prioritize that middle column to just the genes that also significantly altered patient survival. But all we've done so far is just make a bunch of predictions using some assumptions of some observations we made in yeast. How do we actually make sure that this model is accurate? What we can do is we can back test the model. And what that means is we can take the output of our model, pretend we never had access to the real cancer patient data in the first place, rerun our model, make our predictions of chemotherapy outcomes, and then see how often our predictions are actually correct using other real cancer patient data. And as I mentioned before, what we want is for the genes that enhance doxorubicin cytotoxicity, we want those to be underexpressed, and for the suppressors to be overexpressed. So we did that for all the genes we found significant, and we found our model had a 73% accuracy in predicting the direction of the effect of these human genes on human chemotherapy or human patient survival based on what we saw in the yeast. And you might think 73% is pretty low, that's like a C on a test, but to put it into perspective, if this model was purely guessing chemotherapy outcomes, we would have a 1 in 4 chance, so a 25% accuracy. So our model offers an almost threefold increase in that accuracy. So to recap everything this project did, we started with 6,000 genes in the yeast genome. We found 225 yeast genes that significantly alter yeast doxorubicin susceptibility. We found the corresponding 225 human ortholog genes that corresponded to those yeast genes. We used our model to predict real cancer patient chemotherapy outcomes, and then we backtested our model where we found it had a 73% accuracy in predicting these human chemotherapy outcomes. Improvements in future work. One thing we can do in the future is expand the analysis to more cancer patients. Right now, we're only using one cancer patient database. We can only stand to gain from expanding to other databases. And another thing we do is obtain actual treatment information. As I mentioned before, doxorubicin is used to treat breast cancer, ovarian cancer, and lung cancer, but the database didn't tell us how this treatment is actually administered, so we could benefit from knowing how it's administered. Another thing we could do is include other genetic data in addition to gene expression. So right now we're only looking at over and under expression. We could use something like mutation data or protein level data to help us with our results. Another thing we can do is expand to other drugs appropriate for use phenomic analysis. Right now we're only testing doxorubicin. We can use something else called 5-fluorouracil, which is used to treat breast cancer and colon cancer. So we can expand to other drugs and other types of cancer. Lastly, we can conduct prospective analyses. So what that means is we can actually go out to a real hospital and see if using our model does actually increase the patient's chance of survival. All we've done up until now is use past patient data. We haven't really tested it with current patients. And yeah, that's pretty much it. These are my references. Thank you for listening.
Good afternoon, everyone. My name is Dmitry Saznov, and my project is Every Interval at Once, the application of topology to comparative musicology. So my project is on the topic of music information retrieval. This is an interdisciplinary science which is applied in many fields, such as your music streaming services and the algorithms they use, or fields like ethnomusicology for ethnographic study of stylistic influence. So specifically, I target extracting melodic features. So, so far, most computational musicology projects have been using the same few data sets, and often they neglect melodic features because it's hard to extract features from these complex melodic patterns. So that's what I aim to do in my project. So music theory tells us that the circle of fifths is, it's a common tool to construct relationships between notes. So you can, many music theoretical features are constructed on this. So for example, your standard scales like major and minor are basically just 7 adjacent notes on the circle of fifths. Then if we go down each side of the circle of fifths from top to bottom, we get how major or minor something sounds. So for example, going down the right side sounds more major as compared to. And regardless of root note, we can also figure out how consonant a note is, or an interval is. So for example, regardless of the root note, that is a very dissonant interval as compared to. So, and there's also characteristics that don't lie on the circle of fifths, such as chromaticism. But we can construct all sorts of hierarchies and music theoretical principles, such as the standard diatonic scales, as you see on the right there. So how can we compare these sorts of features computationally? So I use the interval distribution. So basically, we represent a song as this distribution. So if we take an example melody, we dissect that into its intervals. And each of those is plotted onto the distribution. So here you see it plotted onto the chromatic circle. Now when we plot it on the circle of fifths, clearly there's significant adjacency relations which indicate a deeper pattern in it. So furthermore, a interval between two notes can be represented as a single spot on a torus. So what this means is that our interval distributions are actually toroidal distributions. So how you can imagine this is that the form of data that was shown before on the bottom, if you're familiar with the Markov matrix, it's essentially that, but as a distribution as a whole. We can wrap that into a torus form as shown in this GIF. So I had to create a distance metric to compare these distributions, so I based it on Earth movers distance. What this does is it cuts up a distribution into several granules and then finds the distance moved times the amount for this granule and sums that for all granules. Finding the optimal path gives us a distance metric. So by doing this, we can alter the cost matrix to do this with the torus, giving us an analogous operation on the interval distribution that I dub interval movers distance. So as you can see here, rather than granules, we operate with the infinitesimal strands of an interval distribution. So in order to validate this, I took the music theoretical metrics defined before, as well as some more, and compared how well it correlates to it. And I had p-values of less than 0.0001 for all of them, which is outstanding results. So the actual applications to music information retrieval, I sourced my data from every noise at once, and then I converted this to MIDI through basic pitch to operate on the melodies. So the total data set was 23,059 songs across 75 genres, the genres that you see here. So after that, I decided to apply it to music mapping, and this is from the principle of the manifold hypothesis, or the principle that dimensionality reduction operates on, which is that high dimensional data has a low dimensional embedding in it. To unravel this embedding, I used UMAP, constructing this map. So each point on here is a song, and the colors are controlled by the music theoretical features. So in this left area is the more major songs, whereas over here are the more minor. Here are the very dissonant songs like jazz, metal, and such, and here are the more consonant, which are like minimalist, electronic, etc. So if you take a look, I filtered it through history, and you notice this top area seems to grow out, which these are excellent results because it shows that we can see the growth of a new musical style over time. If you actually go in and see what songs are there, you'll find there's a lot of electronic and minimalist songs. And if you were at my poster earlier today, you saw not only that, but that we are able to see and hear this map. By randomly regenerating the music through the interval distribution. So by taking the nearest neighbors of any point, you essentially have a recommendation algorithm. Here you see a song by Taylor Swift, and interestingly, the similar genres are not only folk and gospel, but even genres like K-pop. So these results they show statistically and empirically that this is a good measure for melodic features and stylistic influence. So for future work, I'd like to implement this in convolutional neural networks, as well as analyze songs grouped by country rather than genre, predict future trends based on this, and other topological music theoretical structures. I'd like to give my acknowledgments to these people, and these are my references. Thank you.
Oh goodness. Seems I've made a mistake. Here we go. Hi everyone, my name is Raka Pant. Today I'm presenting a project titled The Effects of Color Palette Choice on Advertisement Engagement. To start out, social media has started to take over the advertisement world, and as a result, advertisers have started to spend absorbent amounts of money on advertising. Because of this, we know that the United States spends $365 billion, and the whole world spends about $517. We also know that attention spans are dying. With the rise of TikTok and other short-form content, Microsoft found that in 2000, our attention span was 12 seconds. In 2013, it was 8 seconds, and now in 2024, you can only imagine how much further that's gone down. With social media's reach and engagement, it's important to find small but effective ways to engage consumers in your advertisement content. For that, the first solution I thought of was color palette. There are several color palettes to choose from, including a monochromatic, where we just have different hues of the same color, an analogous, which is a 3-color cohesive color palette, a complementary, which is 2 contrasting colors in every hue, a triadic, which is the 3 triangle colors, a split complementary, which has the 2 opposing colors plus the 2 analogous colors, and then the tetradic, which is a rectangle shape around the color wheel. My objective was to determine whether or not color palette choice really did make an effect on these advertisements and their choices that people made when looking at it. To do this, I decided on a couple of things. Number one, I looked at what items is everybody looking to purchase. Everybody needs to get somewhere, so transportation is a good one. Everybody wants entertainment, so the game industry is another good one. Everyone has to eat, so food. And everyone has to be clothed. Well, so clothing. With that, I needed to look at general necessities and wants. Knowing this, I can kind of separate what color palettes might be more effective. Additionally, gender-neutral purchasing patterns. When designing the advertisements, I wanted to make sure that everything was as neutral as possible. Additionally, I needed to decide on my color palettes, 2 colors versus 3. For that, I chose complementary as the baseline, triadic as the next 3-color contrasting, and analogous as the 3-color cohesive. Additionally, I looked at what advertisements I could use on Canva. With that, I found general generic templates on Canva, took the main color in the advertisement and plugged it into a calculator, and then created the 3 advertisements in accordance to those color palettes. I then asked my participants 2 questions. On a scale from 1 to 10, how likely you'd be to click on the advertisement, and between the 3 advertisements, if they could rank first, second, and third. That allowed me to run a Kruskal-Wallis test and a chi-squared goodness of fit test. With that, I was able to see that for the food industry and the clothing industry, the chi-squared value was significantly low, with some clear trends in complementary and triadic winning out, and triadic winning here, and that the Kruskal-Wallis test showed a significant result. With that, I know that you can reject the null hypothesis for the food industry specifically, meaning that color palette really does play an effective role. For the other industries, clothing was the only one that was affirmed by the chi-squared test. Otherwise, every other null hypothesis was failed to be rejected. Another future work that I could look into is the call to action button. Those flashing buttons that you see on the side of your screen that are slightly annoying might draw more attention than expected. So that's another thing to look into. Additionally, separating needs and wants more clearly. There's certain things that can be seen as wants in some areas and needs in other geographical areas, and that's another thing to look into. These are my acknowledgements. I'd like to thank all these people, and here are my citations. Thank you, everyone, and I'd be happy to answer any questions.
Hello, everyone. My name is Eli Mrug, and my project is on the computation of attracting regions for attracting and parabolic fixed points. So my project is in complex dynamics. And complex dynamics is essentially the study of the repeated iteration of some complex function on an initial point, and seeing the dynamics of that point as time goes forward. And so this generally you can find applications in discrete time systems like in physics or in chemistry. But the important thing is that under these mappings, your points can have different types of behavior. You can have points that are in the Fatou set, here shown in blue, that have non-chaotic dynamics and approach some sort of fixed orbit of the function. So here the point goes to the origin. You can also have points in the Julia set, here shown in red. And these points behave very chaotically. Changing them even slightly will completely change their end-state dynamics. So you can see this one goes all over the place here. If you draw the Julia set, here in black, you can partition the plane into multiple distinct Fatou components. So here there's an inside and then an outside around it. If you look at each of these Fatou components, eventually all of them will be centered around some fixed point of your function. So that's f of z is equal to z. And if you look at each one of those fixed points, then the dynamics around them can be determined by the derivative of the function at that point. So let's look at some examples of that. So if the absolute value of the multiplier is less than 1, you get this attracting case here. And in this case, the fixed point is at the very center, and all of the points attract towards it. If the absolute value is equal to 1, and it corresponds to a rational rotation, then you get this parabolic case. And we'll get into the dynamics of this one a bit more later. Finally, if it's an irrational rotation, then you get either a Siegel disk or a Kremer point. Now, even proving that some of these exist can be very, very difficult. We don't even have images of a Kremer point yet, which is kind of interesting. So we won't get into them in this project. So my motivation behind this project is that normally when you're trying to figure out where a given point will end up, the problem is that how do you do that? Because it could take thousands, it could take millions, or it could take even more iterations before you get even close to the fixed point. The normal strategy here is to just iterate each point a certain amount of times, and if it ever gets close to a cycle, just assume that it attracts. The problem is defining what close enough isn't easy. If you escape too early, you risk misclassifying points, and if you escape too late, then you've wasted valuable computation time. So the goal for my project is to establish reasonable bounds around each fixed point within which all of the points will attract. So let's get into a bit of the math on this. So for attracting fixed points, we have this inequality, and this essentially says that around each such fixed point, there must be some radius that has the quality that we're looking for. And through a lot of algebraic simplification, eventually we can get it into this form down here. And here, t is this function that takes the sum of the absolute values of the coefficients of a polynomial. And once we have this, we can solve it relatively quickly using something like Newton's method. So let's talk about parabolic fixed points a bit more. So parabolic fixed points are a lot more complicated. It actually depends on the direction you come at them from. So, for example, if the parabolic fixed point is here in the middle, if you come at it from this direction v1, v3, or v5, then you're attracted towards it. But if you come from v0, v2, or v4, then you're repelled away. So the direction you come from has an effect. The way we get around this is that we establish the transformation to an alternate plane called the W plane. And that transformation is defined this way, where c and n are constants depending on the function and the fixed point. From here on, we can conjugate our original function in this W plane, and we find that it's asymptotically equal to W plus 1 up to some error term. If we can bound this error term, then we can say for sure that the real part of this point will eventually go to infinity. Hence, the point itself will go to infinity. And as we saw here, if W goes to infinity, then Z tends to 0, and we've gotten towards the fixed point. So essentially, we just want to find a radius outside of which this will hold. And we can do this by expanding it and doing a lot more algebra. This one's even less fun. But eventually we get to this final inequality, which we can solve for, and again, reasonably quickly get a value of r for it. For my implementation of all of these methods, I used C++ due to the speed of the language as well as the low-level control that it provided. My algorithm was to use a pixel scanning approach, splitting the complex plane into a rectangular grid and then sampling each point on that grid. So finally, let's get to some of the results of this. So for all of these results, on the left will be the Fatu-set plot. This is a plot of the complex plane that shows where each of the initial starting values will end up. So here, the colors tell you which of the fixed points it'll go to. So for example, there's a fixed point here, yellow, one here that's red, and one here that's blue. And then the lightness or darkness tells you how long it takes. So here, the points that are white were classified almost instantly, and the dark ones took a bit longer. So on the right is an iterations versus time graph, where my method is plotted in black, and the normal method is plotted in red that you would use. And as you can see in this case, as you increase the iterations past about 30 or so, my method becomes much, much faster. And that gets more prolonged, because in fact, here in this case, it classifies all of the points. So increasing the maximum iteration doesn't have any effect. Here is a test case for a parabolic fixed point. The previous one were attracting ones. So this is just a simple example of that. And here you can see that, again, my algorithm is much faster overall. It doesn't classify all of the points because some of them take a very, very long time to attract. But again, it is much better. My third test case is this very complicated function with 3 parabolic fixed points. And so the problem here now is that even finding all of those radii from before is very computationally heavy. And so this results in a very large overhead time between my method and the normal one. However, since I'm using a more efficient algorithm, eventually, with enough iterations, my method will still be faster. So overall, in the attracting case, my algorithm is much, much faster. It requires almost no iterations, since the radii can be computed fairly quickly. However, in the parabolic case, where you have to compose your function multiple times and then calculate all of these radii over again, it gets a bit slower. But the main takeaway here is that since you only have to calculate each of these radii once for a given function, as you do more work on the same function, my method becomes more and more efficient. In fact, usually when you're computing images for this, you'll use about 10 to the 4, 10 to the 5 iterations, and in all of these cases, my algorithm is better here. So I would like to acknowledge these people. Thank you.
Hello everyone, my name is Ananya Mohanraj and my project is titled Curvature of a Flow Volume Curve and its Utility as a Diagnostic Marker for COPD. COPD is more formally known as chronic obstructive pulmonary disease. So what is COPD? COPD is a collection of lung diseases characterized by airflow obstruction, which is just the narrowing of the airways. COPD is primarily caused by smoking, which leads to irritation and inflammation, causing permanent damage to the lungs. Symptoms of COPD include shortness of breath, wheezing, coughing, mucus buildup, and more. These symptoms can be treated, which can prolong the progression of the disease, but it cannot be cured. In 2019, COPD was the 3rd leading cause of death worldwide. Currently, 14.2 million Americans are living with a diagnosis of COPD. On average, 150,000 Americans die every year due to COPD. That's 1 death every 4 minutes. A study of 10,000 patients found that 67% of diagnoses are considered late. And what I found the most surprising is that 70% of COPD worldwide is underdiagnosed. Underdiagnosed means a patient receives a diagnosis either less severe than what they have, or they don't get a diagnosis altogether. For such a prevalent disease, to go so underdiagnosed is concerning. So let's look at how COPD is being diagnosed right now. The most common form of diagnosis are pulmonary function tests, or more specifically, spirometry tests. Spirometry tests measure how much air a patient can breathe in and out of their lungs, as well as how long it takes them to do that. From this, the current diagnostic metric looks at 2 values, FEV, which is the forced expiratory volume, just how much air the patient can breathe out in total, and FVC, how much air the patient can breathe out in 1 second. Then a ratio is found between these 2 values and organized into gold stages based on the severity of COPD. Additionally, there's gold -2, who are healthy patients, gold -1, which is PRISM, preserved ratio impaired spirometry. These patients have lung impairments but don't meet the spirometry definition of COPD. And then there's gold 0, which are smokers that exhibit symptoms of COPD but do not have the disease. Knowing all of this, I wanted to see if I could use these same spirometry tests but interpret them differently to potentially decrease this underdiagnosis. I wanted to see if I could find an association between the curvature of flow volume curves produced by the spirometry test and the progression of COPD. In order to do so, I had the spirometry test for 7,780 patients, each patient containing hundreds of points of volume and time. So why did I use curvature? Curvature represents the rate of change of flow versus volume. Through using curvature, we can get an understanding of the entirety of the patient's breathing, instead of the current method, which just looks at how much air the patient breathes out in 1 second and how much air they breathe out total. For the purpose of my project, I defined curvature as the summation of the absolute value of the second derivative of every point on the flow volume curve and the 2 points before and after it divided by the total number of points. I hypothesized that a higher curvature value would be associated with a less progressed form of COPD, since a high curvature value would be indicative of better lung function and vice versa. I have provided samples of each of the gold stages, including their original flow volume curve in blue and the calculated curvature in orange. On the top right, you can see a gold 1 patient, which is the most mild form of COPD. And on the bottom right, I have gold 4, which is the most severe form of COPD. Just through a visual analysis, you can see that gold 1 and 4 have drastic differences in their curvature. So I started by looking at the relation between curvature and gold stages. As you can see, there definitely is overlap between the curvature values of the different gold stages, but as we go from gold 1 to gold 4, we do see a decrease in curvature supporting that initial hypothesis. Next, I wanted to be able to differentiate between these calculated values of curvature, so I separated my curvature values into quartiles. Quartile 1 on the left contains the lowest of curvature values, and quartile 4 contains the highest of curvature values. Then, I looked at the average curvature values for each of the gold stages. As you can see, gold 1 has an average of 85, and as we go down the gold stages, we can see that there is a decrease, going from 85 to 70 to 57 to 46. However, I needed to make sure that there was a statistically significant difference in these averages, so I ran a one-way ANOVA test with a significance value of 0.001. I got a p-value of almost 0, confirming that there is a statistically significant difference, but I needed to see where these differences existed, so I ran a post-hoc Tukey test, and of the 21 comparisons, only 6 failed to have a statistically significant difference. Next, I wanted to look at the distribution of gold stages within each quartile. Soon into this process, I realized I couldn't make sense of these numbers because different gold stages had different amounts of participants. Gold -2 only had 77 patients, whereas gold 0 had over 3,000. So I had to find a way to standardize these numbers. I found the relative frequency of quartiles within each gold stage. Gold 1 fell predominantly into quartile 4, which contains the highest of curvature values. Gold 4, the most severe form of COPD, fell predominantly into quartile 1, which contains the lowest of curvature values, once again supporting that initial hypothesis. So, knowing all of this, how can we use curvature? In order to observe how curvature could be used, we'll look at gold 0 patients, who are the smokers that exhibit symptoms of COPD but do not have the disease. The relative frequencies are once again shown on the screen. As you can see, 13.82% of these patients fell into quartile 1, which we have established is associated with gold 4, the most severe form of COPD. Although we cannot use this to diagnose these patients, they can be prompted for further evaluation, like CT scans or chest x-rays. COPD cannot be cured, so early detection is crucial. Through treatment, these patients can prolong the progression of their disease, but with such severe underdiagnosis, it's important that we take steps to improve where we can. In conclusion, I found that there is an association between the curvature of flow volume curves and the progression of COPD. Higher gold stages fall into lower quartiles, and lower gold stages fall into higher quartiles. This could be a significant addition to current diagnostic criteria based on spirometry. In the future, I would like to utilize different definitions of curvature. I would like to validate this in a larger control with more cohorts. And finally, I would like to test this on a volume time curve. These are my references, and I would like to thank these people and thank the audience for their time. Thank you.
Good evening, everyone. My name is Julia Downs, and today I'll be presenting my analysis of the effects of extreme heat and harmful pollutant concentrations on hospitalizations and emergency department admissions in individuals with asthma. So, as a result of industrialization, urbanization, and combustion engine vehicle development, air pollution is constantly being emitted into our atmosphere. According to the EPA, over 66 million tons of air pollution were emitted into the US atmosphere in 2022 alone. Those with pre-existing medical conditions are particularly susceptible to the negative effects of long-term exposure to these pollutants, especially those with respiratory conditions. Asthma, one of the world's most prevalent chronic non-communicable airway diseases, is characterized by inflammation or obstruction of the airways. According to the CDC, more than 26 million Americans live with asthma, being 1 in 12 children and 1 in 13 adults. This accounts for 1.7 million emergency department admissions, 439,000 hospitalizations, and over $50 billion in healthcare costs yearly. This here is a depiction of a normal airway, an asthmatic airway, and an asthmatic airway during an attack. As you can see, the asthmatic airway has inflamed walls, and when under an attack, these smooth muscle cells tighten, causing air to get stuck in the alveoli, leading to difficulty breathing. The goal of this project is to analyze how hospitalization and emergency department admission rates for individuals with asthma are impacted by various environmental pollutants and extreme temperatures. The pollutants I studied were sulfur dioxide, ozone, nitrogen dioxide, and PM2.5, characterized as particulate matter with a diameter of 2.5 micrometers or smaller. And that can be organic compounds, small metallic particles, things usually emitted by smokestacks in urban areas. I hypothesized that there will be a moderate to strong positive linear correlation between all sets of 2 variables, of which there are 10, being emergency department admission paired with environmental factors, and then hospitalization paired with environmental factors. The first thing I had to do was find my general area of study, which ended up being Arizona, as I was able to gain access to health records from the EPHTN, the Environmental Public Health Tracking Network, one of the only publicly available health databases sorted by sub-county and condition. From there, I had to narrow it down even further to a specific area of study. So I did that by gathering concentration data for each pollutant from the EPA, and then I used the QGIS mapping program, a mapping program often used for environmental research visualization, to create these concentration gradient maps to find where each is most concentrated. I made one of these for each pollutant for each year 2010 through 2020, as that was my time period of study. And as you can see, okay, well, you can't really see the name of the city, but that is Phoenix, Arizona, which isn't very surprising, as that is the largest city in the state and most populated. So from there, once I figured out my specific area of study, I gathered temperature data from the NOAA, and I gathered the health data from the previously mentioned tracking network. That data was then sorted into spreadsheets pairing environmental factor with either emergency department admission or hospitalization. And then analyses were run to determine linear regressions, correlations, graphs, and other statistical components, which can be seen here. Here are the graphs for the emergency department admissions, and there are pretty clear relationships between all sets of 2 variables, either being positive or negative, and then the same for hospital admission. From that, I could get the R value and R squared value. R value, or correlation coefficient, is the measure of strength between a relationship between any two variables. And the R squared value is the proportion of variance in a dependent variable caused by an independent variable. What all of that means is basically that shows the strength and direction of a correlation. And the most notable are sulfur dioxide and nitrogen dioxide with hospitalization and emergency department admission, and PM2.5 and ozone with hospitalization. In conclusion, the data show a moderate to strong positive linear correlation between certain pollutants and hospitalization and emergency department admission for those with asthma. In terms of future work, I would like to consider different socioeconomic variables that could affect whether or not an individual can go to the hospital or the emergency room for, say, passing out from an asthma attack. That can be health insurance status, location of residence, occupation, things of that nature. I would also like to expand my area of study. As Phoenix has a very specific climate, it's very dry and it's very hot. Maybe looking at somewhere like Florida, that's still hot, but it's very humid and has a lower elevation. Here are my references. And I would like to give special thanks to Dr. Marian Karimi at the UAB School of Public Health for being my mentor, Ms. Hung-Sin Chin and Dr. Leanne Kinnunen for being my faculty advisors, the rest of the math science faculty, and my family and friends. Thank you very much.
One, two, there we go. Gotta make sure. It's a quick rhythm. Thank you. Good evening, everybody. I'm Wade Lewis, and I'll be presenting AI versus casual and professional pilots. Is there a difference? Now, for some background into jet fighter aircraft, there's generations to it. We're currently on the 4th, 5th generation. But the 6th generation is coming up, and it's going to add AI, artificial intelligence. Now, for a definition of professional casual pilots are people trained by the United States Air Force. Casual pilots, people who are not trained by the United States Air Force. They can be commercial pilots, but they are not trained by the USAF. So for pros and cons of AI when compared to humans, some pros: increased G tolerance, right? A human, when they're in the cockpit and they pull too hard, they're going to black out after 9 or 10 Gs. AI can go up to 12, 15. It's limited based on the aircraft, not the pilot. It costs less over time. It costs millions of dollars to pay for USAF training, and reduced number of mishaps because AI, right, won't fail as much as humans. Humans fail a lot, and that is the cause for a lot of aircraft crashes, even in the commercial space. But some cons for that is it can be jammed. Humans, you can't jam humans, but you can jam electronics, and it's out the sky. Increased maintenance costs because we're working specifically on AI. AI can't take care of itself. Humans can take care of themselves with their own money. And it's semi-autonomous. We don't have autonomous AI that can think on its own. It can only do what it's programmed to do. So for my materials and methods, I use digital combat simulator, sometimes used to train United States Air Force pilots. And what I would have the participants do is download that, go to the custom mission editor, choose 2 similar aircraft, and I'll show you 2 right here, Russian MiG-29 and the American F-16, very similar in performance, but if you know the niches, you can win the fight against the other one. Make sure they set them a kilometer or 0.62 of a mile apart for a dogfight scenario. Dogfights happen close, that's why it's called a dogfight. Start a mission with the AI, against the AI, and first to get the 3 kills wins. Now, just to clarify kills, 3 kills is when you destroy the AI, right, it's on fire, and their plane's going down, and they no longer have control 3 times. That counts as a win. Now, if you don't have control of your aircraft, then you lose. And that was the case for basically everybody, except for 4 people. So the casual and professional pilots lost across the board with only 2 from each actually winning against the AI overall. And I use this table right here, which shows the same thing as the graph, to do a Fisher's exact test, right? Since I have a small sample size, I can't use chi-squared, I have to use Fisher exact, and it came out with a significance of 0.253, a p-value of 0.253, which means there is no statistical significance in between casual and professional pilots. Now, visually, because I watched these people do it live with my own eyes, the professional pilots did have better knowledge of the aircraft, of dogfighting in general, and just airplanes in general, and they could use that to beat the AI. To wrap this up, AI, more precise, more accurate, G-force tolerant, could utilize all those G-forces. That's how the AI won against the humans. There's no statistical difference. For future work, I like to test professional pilots with different flight times because there is a difference between a pilot with 0 hours to 400 hours. Using actual aircraft instead of a simulation, of course, that would be more accurate to real life situations. And autonomous AI that don't require coding. It doesn't go based off what it is coded to do, but it can come up with its own solutions to its own problems at the current time. I'd like to acknowledge family and friends, Dr. Flournoy, Mrs. Chen, Dr. Uoya, the ASFA community, and my mentor, James Brooks. Here's my references, and I'm done.
Can you hear me?
No.
Oh, what about now?
Yes.
Oh, all right. So, my name is Alexander Kim, and my project was evaluating the association between airway wall thickness and ECAC. So first, you might be wondering, well, what is ECAC? ECAC stands for excessive central airway collapse, and in this case, we're examining ECAC disorder. So ECAC is typically diagnosed by 50% or more reduction in the airway area, 50% or more from inhalation to exhalation. And that's not very good because it gets kind of hard to breathe when your airway area decreases by that much, hence why it's associated with higher respiratory morbidity. Another problem with ECAC is that it's very commonly underdiagnosed. It doesn't have many visible initial symptoms, and the symptoms that we can observe are very similar to the ones you might see in other common respiratory diseases, such as COPD or asthma. And so the goal of this project is to find an association between airway wall thickness and the likelihood of having ECAC. So that way we can use that association to gauge a patient's risk of potentially having the disorder. So our research question is there an association between airway wall thickness and ECAC? And our hypothesis is that yes, there is an association between airway wall thickness and ECAC, where a thinner airway wall results in a greater risk of having the disease. So in order to actually answer my research question, I had to collect data. And to do this, I got a database of CT scans from a larger study called COPD gene cohort. And I will look at each CT scan through a medical imaging software called ITK Snap. And the CT scans I look like will look like this image over here through the program. These kidney bean-shaped objects are the lungs. Over here is the esophagus. And over here you can see our point of interest, the airway. And so what I would do to actually measure the airway wall thickness is I'd zoom in really close to the perimeter of the airway, and I could see the actual wall because it would be significantly lighter in pixel coloration than the surrounding area. And ITK Snap lets me draw a line from one point to another and tells me the actual real-life measurement of that line. So I would repeat this process for the up, right, down, and left sides of the airway. And I did this 120 times for each side, and I found the mean and standard deviation for each side's airway wall thickness. And then, once I collected all my data, I was able to apply my statistical methodology. First, I characterized the data set through descriptive and comparison statistics, and used bivariate comparisons with a two-tailed t-test for continuous variables that have numbers in them, and chi-square test for categorical variables that don't have numbers in them. And then, once I actually constructed my data table and characterized my study subjects, I created a multivariable logistic regression model to actually answer my research question. I used this model to evaluate associations between airway wall thickness and ECAC status, and I adjusted for covariance. Remember this part, that's important later on. And I did this through 95% confidence intervals, which were constructed after estimating odds ratios. You can see the characteristics of the data set in this table over here, and you can see the multivariable logistic regression model over here. So first, big question, what's an odds ratio? An odds ratio is the probability of an event occurring after a change over the probability of that event occurring before the change. In this case, that event that we're looking at is whether or not the subject in question has ECAC. And the change is a 0.05 millimeter decrease in the airway wall thickness. And we looked at this for each side and the average. Now, this confidence interval and this confidence interval do not intersect with that odds ratio line of 1, indicating that they are statistically significant, where 95% of the time, if we were to take a sample, we would not expect it to have no association with a decrease in airway wall thickness and having ECAC. And however, you will notice over here that they do intersect with that line, meaning they are not statistically significant. However, if you would also notice all of these black dots indicating the mean of each confidence interval are on the right side of the line, showing that in the general trend of our results do support our hypothesis in that a thinner airway wall thickness is generally associated with a higher risk of ECAC. And so the conclusion we can draw here is, yes, our hypothesis is supported. We can look at airway wall thickness and see a thinner one and have it be a reasonable suspicion for ECAC. However, there are discrepancies in statistical significance for different sides of the airway wall thickness. And you might be wondering, why is that? Well, the reason for that is because earlier, as I told you, we adjusted for covariance. And that's basically accounting for the demographics of our relatively diverse data set and isolating for those demographic variables. And the way we do this is we have our 120 study subjects, and then we split them off into niche groups, like white, female, current smokers, or obese, and you'll end up with around 16 of these groups. So at first you have a reasonable sample size of n equals 120, but once you split them off into each of these niche groups, around 16, then you'd have around 10 study subjects each. So we quickly go from a relatively large sample size to a relatively small one, hence why it's kind of hard to get statistical significance and why we see that discrepancy over here. But the fact that we got statistical significance for the left and average airway wall thickness shows the robustness of our results in supporting our hypothesis that airway wall thickness is associated negatively with having ECAC. So future work, we want to address the discrepancies in statistical significance and confirm statistical significance for all the sides of the airway wall. We would do this by essentially repeating the study, but with a much larger sample size. Before I conclude, I would like to give my acknowledgments to the following people: Dr. Surya Bhatt, my mentor, Dr. Sandeep Boduluri, Mr. Vivek Stanam, Dr. Cecil Fernoy, and Ms. Hung Sin Chin, my faculty advisors, and my mom and dad.
evening, everyone. My name is Cynthia Liu, and my project is titled The Effects of TLR7 Stimulation on Mitochondrial Complex 1 Activity of Autoimmune B Cells. So my project focuses on processes that occur in systemic lupus erythematosus, which is abbreviated as SLE. So what is SLE? So SLE is a form of lupus, which is a chronic autoimmune disease, and it causes things like skin rashes, fatigue, and it even includes long-term effects, including arthritis, seizures, and lung, heart, and kidney failure. So SLE is present in over 200,000 adults in the United States, and what's interesting is that over 90% of these adults are female. So you may be wondering what causes this female sex disparity, and the answer is we don't really know. So scientists have a lot of different hypotheses, including hormonal influences, dysregulation in lymphocyte activation, as well as defective X chromosome inactivation, but there isn't one specific reason yet. This is similarly, this is the same for the disease as a whole. So scientists don't really know what causes the disease in general, but they do believe that it is linked to environmental, genetic, and hormonal factors. So the linkage that I focused on was the connection found between dysregulation of energy production pathways and inflammation in SLE B cells. So that's what I looked at in this project. So specifically, I looked at complex 1. So complex 1 is the first enzyme in mitochondrial electron transport chain. And the electron transport chain, or ETC, it generates ATP, which is energy for your cells to use. So complex 1 has been found to have increased activity in SLE B cells, which is why I chose to look at it. Additionally, like I mentioned earlier, dysregulation of this energy production pathway has been shown to be involved in the progression of SLE. So to kind of model the effects, the activity of complex 1, I stimulated the toll-like receptor 7 pathway, or TLR7. So TLR7 is a protein, and it's involved in, again, the progression of SLE and other similar rheumatic diseases. And in order to stimulate TLR7, I used its selective activating ligand called R848. And basically, R848 activates type 1 interferons and cytokines that activates the immune response and stimulates TLR7. So the objective of my study was to determine changes in mitochondrial complex 1 activity in the female SLE B cells. And I did this using reverse transcription real-time quantitative PCR, which I'll just refer to as either RT-PCR or qPCR. They're interchangeable for the purpose of my project. So my hypothesis was that after I stimulated the TLR7 pathway using R848, the mitochondrial complex 1 activity would increase. So that leads me to my methodology. So the first part of my methodology was creating primers for the complex 1 genes that I chose. So what were those genes? So I looked at a heat map of some of the most upregulated mitochondrial genes in SLE B cells, shown in this figure here. So as you can see, here. So as you can see, the ones in red are the more upregulated ones compared to the ones in blue in this column. So as you can see, the complex 1 genes here are highlighted, in very bright red. So those are the genes that I chose to use for my project because they were upregulated in female SLE cells. So those genes were MDFA1, FA13, FA3, FB1. Yeah, those are the 4. So this is a flowchart of the process of my primer designing process. So the first thing I did was sequence my 4 complex 1 genes using the NIH genetic database. I then designed the primers using the Primer 3 software, and then I validated these primers using the NCBI BLAST software. So these were the results of all of those steps. So these are the primers that I designed for the genes, and then we ordered these primers from a DNA oligosynthesis company. So then I used these primers in the second part of my project, which was the actual RT-PCR portion. So this is again another flowchart of the second part of my project. So after receiving the B cells that were treated or not treated with R848, I extracted the RNA, I turned it into complementary DNA, and then I used that as well as the primers I designed for my PCR. So essentially PCR, or polymerase chain reaction, it amplifies DNA products so that we can make observations about the initial template strand of DNA. So the difference between normal PCR and the RT-PCR that I used is real-time PCR measures the amount of product after every single cycle, or after every single cycle, instead of just at the end of all of the reactions. So this allows for a more precise and more accurate measure of the initial gene expression levels. So the qPCR method that I used a fluorescent dye. In my case, it was called cyber green, and this fluorescent dye binds to double-stranded DNA throughout the reaction. So as more cycles progress and more DNA is created, more of that dye will bind to the DNA, and then the machine will excite the fluorophores in that dye, causing it to emit fluorescence. And that is what the machine measures to figure out what the level of gene expression is. So figure 5 here shows an example of one of my results after a PCR. So the way I actually quantified the gene expression levels was I set a threshold fluorescence unit or amount. So that line across the bottom here is that threshold fluorescence. So the cycles that took a higher amount of the samples that took a higher amount of cycles to hit that threshold fluorescence. So like for example, some of these samples, that means that they had a lower initial amount of DNA because they took a higher amount of cycles to hit that threshold. Oh, sorry. But then the cycles on the left here, which took a lower amount of cycles to hit that threshold, means that it had a higher amount of initial DNA. So I used these threshold values in order to quantify relative gene expression for my stimulated and unstimulated groups. So these graphs show kind of the results of the amplification curves. So as you can see, graphs A, B, C, and D were the 4 complex 1 genes that I looked at. So the blue bars were the unstimulated control groups, and the green bars were the R848 stimulated groups. And so you might be wondering, if I had 4 genes, why there are 5 graphs on the screen. So this last graph here, LDHA, is lactate dehydrogenase. It's a different gene. And the reason I chose to look at this gene was after I started getting some of these results back from the first 4 complex 1 genes, I started noticing that there was an increase. The green bars are, for the most part, higher than all the blue bars. And so I was wondering if the same thing or a different thing occurred in other energy production pathways. So I looked at glycolysis, which is a different step in cellular respiration. And specifically, I looked at lactate dehydrogenase, or LDHA, which is a part of the glycolysis pathway. So that's why I looked at LDHA, and then I repeated all of the previous steps and created this graph. So figure 7 is a summary of basically all of the previous graphs that were shown in the last slide. So again, the orange bars are the unstimulated groups, and the purple bars are the ones that were stimulated using R848. So as you can see, I set a significance value of 0.05, and 4 out of those 5 genes showed a significant increase after I stimulated TLR7. So my conclusion was that stimulation of the TLR7 receptor using R848 caused a significant increase in the complex 1 genes NDFA1, 3, FB1, as well as the glycolysis gene LDHA, but not in the complex 1 gene NDFA13. So for this project, I used all female cells. So in the future, I'd like to expand this as well to male cells, because we do know that there is that 9:1 ratio of SLE in women to men. So I'd like to see if a similar thing presents in the energy production pathways of these cells. Additionally, now that we know that there is that linkage between the complex 1 activity and the TLR7 stimulation, I would like to see if there is actually an increased immune response because of that increased energy production. And I would do that by measuring the gene expression levels of immunoglobulins, which are just antibodies. So instead of measuring the complex 1 expression, I would measure antibody expression. I'd like to acknowledge Dr. John Mouse, Dr. Hui-Chun Su, and Catherine Sullivan at UAB, who are my mentors, as well as Ms. Vincila Gimlon, Ms. Hung-Sin Chin, who are my ASFA faculty advisors, and of course my family and friends for all their support. And here are my references.
Can you hear me? Yes. Okay. Hello, my name is Varsha Vinoy. I'm a student in the Alabama School of Fine Arts. Today I'll be presenting my project on the applications of plasma treatment on the polydopamine-coated 3D printed polymer scaffold. As an introduction, my project is mainly focusing on polydopamine, also known as PDA. PDA is a bio-inspired material that was first found in sea mussels. It has since been used to coat the surfaces of different materials in order to increase the chemical reactivity as well as its surface adhesive properties. There are several applications of polydopamine, more notably and recent includes wound healing, bone repair, regeneration, drug delivery, and so much more. For my project specifically, I'm looking into the chemical process from dopamine to polydopamine via oxidative polymerization. This process is synthetically developed using the wet chemistry method. However, this method has its set of disadvantages, given that it's inconsistent with its results, as well as it is slow, taking roughly 10 hours to several days. And all of these factors culminate to this process not being viable for long-term usage. There were attempts to solve this problem, such as optimizing parameters or utilizing oxidizing agents. However, these solutions had its own set of disadvantages, such as if you utilize oxidizing agents, it has the potential of being toxic. This leads me to my objective, which is to develop a scalable and greener safe process that would enhance the effectiveness of the polydopamine coating on biomaterial surfaces. In that I hypothesized that the usage of plasma would better enhance the effectiveness of the polydopamine coating on biomaterial surfaces. In order to test my hypothesis, I created the following procedure consisting of 8 steps. I first 3D printed 24 PLA scaffolds from a given 3D printer. I then prepared the stock solutions of dopamine, copper sulfate, and the mixture. And I separated the PLA scaffolds into 8 groups, having a total of 3 trials. And these groups were based on whether it was with plasma or without plasma, and the type of solution, including no solution. For the PLA scaffolds associated with the solution, I would soak the PLA scaffold into the solution for 5 minutes. After the 5-minute mark, I would then dry it up using chem wipes. And then I would subject all 24 PLA scaffolds to the air plasma treatment for 10 minutes. And after the 10-minute mark, I would subject only 12 of the PLA scaffolds associated with plasma to the hydrogen plasma treatment. From this, I got the following results. As you can see here, this is the qualitative analysis. And you can see that without plasma, there's a consistent beige color and there's not much of a change. Compared to with plasma, you can see somewhat of a difference in color, mostly of a brownish gray tint color. But I wanted to do much more microscopic way rather than just this the previous evidence alone. So what I did was I looked at it in the microscopic level by utilizing laser scanning microscopy, and you can see that without plasma, there's not much of a defined layer compared to with plasma, in a way showing enhancement. I then wanted to further the microscopic level by utilizing scanning electron microscopy, which is used for analyzing the morphology of the PLA scaffold. And you could see that without plasma, there's not a lot of deposition and the texture tends to be a lot more rough. Compared to with plasma, you can see a lot more deposition and smooth textures, thereby showing enhancement. But all the previous evidence as shown before and previously were all qualitative data and not quantitative. So I wanted to utilize the X-ray photoelectron spectroscopy, which looks into the chemical composition of the surface. And you can see that there are 3 images, which is the control, dopamine, and mixture case. You can see that with plasma, there's an increase in counts per second, thereby showing the amount of scans for each of the elements. And that in a way shows enhancement. And another thing to notice is that from the control, you can see only carbon and oxygen being emitted, and for the dopamine and mixture case, you can see introduction of nitrogen, which is very important for my next set of results. For this is the statistical analysis of what I did. Since the percentage of nitrogen was introduced, I used it as a sort of metric measure to quantify the enhancement of the polydopamine coating. And you can see in both the dopamine and mixture case, I took the ANOVA test to determine the significant difference between the percentage of nitrogen versus the usage of plasma with and without. And in fact, there was statistical difference between the percentage of nitrogen and the usage of plasma with and without. In conclusion, I was able to support my hypothesis that the plasma-treated scaffolds have shown greater enhancement of the polydopamine coating compared to the non-plasma-treated scaffolds. For future works, I would like to adjust different processing parameters, such as increasing the dopamine precursor and decreasing the exposure time, as well as power. I would also like to look into the biomineralization potentials of the PLA scaffolds to make further advancements in bone repair regeneration. I would like to acknowledge the following people, and these are my references. Thank you for your time.
Hello? Can everyone hear me? No? Okay. Let's see if we can turn it on. Okay, is it on? Okay, good. Hello everyone, my name is Nicholas, and today I would like to talk about my project, where we use special molecules called ketone esters to slow vancomycin and 41 mammary tumor growth. And so over the course of this project, I first want to give a little bit of introduction as to cancer metabolism and what ketone esters even are. Afterwards, I want to talk about the dietary intervention we used, eventually building up to the conclusions we made and potential clinical applications. So first, let's talk about cancer cells. So cancer cells are characterized by two main things. First, high glucose dependence, and second, high lactate production. So, what does this mean? Well, through the increased lactate production, it basically allows the cancer cells to make new blood vessels. This is known as angiogenesis, meaning that it can take in new nutrients. Second, through the increased glucose uptake, it basically allows the cancer cells to outcompete regular cells for the same resources, meaning that it can grow at a faster rate. And so kind of the guiding question we had here is how can we inhibit the metabolism of these cancer cells while doing the least amount of harm to the cancer patient? And so current methods of doing so rely heavily on nutrient restriction. One such method is by using carbohydrate restriction, which reduces the amount of carbohydrates and glucose for the cells to grow. And second, ketogenic diet, which is a modified carbohydrate restriction diet whereby you increase the amount of fats and you also decrease the amount of carbohydrates. However, the problem with these methods is that they often result in a lot of nutrient stress and a lot of stress on cancer patients. And so what we wanted to do is sort of bridge the gap. More specifically, what we want to look at is a ketogenic diet. The ketogenic diet, when you do reduce the amount of carbohydrates and increase the amounts of fat, it basically forces the body to break down the fats into special molecules called ketones. Cancer cells cannot metabolize the ketones, but regular cells can. And so more specifically, what we want to do is exogenously introduce the ketone esters, acetoacetate, and beta-hydroxybutyrate without forcing nutrient restriction. And more specifically, we hypothesize that through the introduction of these ketone esters, that we reduce 41 mammary and vancomycin tumor progression while maintaining muscle mass. So, which cancer cells do we use? Well, we use the 41 and Vanca cells because they are highly glycolytic and because they have varying glycolytic abilities. What does this mean? It means that they are representative of an aggressive tumor model. Afterwards, we looked at our experimental design. So for the in vitro experimental design, in other words, with the lab plates and everything, we created 4 different role plates. 41 regular glucose, 41 low glucose, Vanca regular glucose, and Vanca low glucose. And so each one was differentiated by the differences in the rows. So we had acetoacetate, ECAC, beta-hydroxybutyrate, and then we had a combination of both, and then we had 2 different controls. Afterwards, we looked at our in vivo design, and so basically what we did is we started the mice on a control diet, we got the body weights, and then afterwards we got pre-surgery weights. Why? Because we wanted to exclude any of the mice that was either too light or too heavy. Afterwards, we started a tumor challenge. In other words, it's a nice way of saying we gave the mice cancer. And then we randomized the mice either to a control diet, which we can see right up here, the composition, or the diet with the ketone esters, which we can see right there. Afterwards, we measured bioluminescent imaging, which basically allows us to look at metastasis, blood ketone concentration, and then finally, takedown. So, for the in vitro design, let's look at this. We actually see a statistically significant difference between the control and the acetoacetate and beta-hydroxybutyrate. However, for the Vanca cells, we unfortunately do not see a difference. Why is this? Well, it could be due to the fact that they have varying glycolytic abilities and there are different types of cancer cells. And so that could explain the differences we see right here. And so afterwards, we wanted to bring it back into the mice that we were studying. And more specifically, we want to look at the blood ketone concentration. So we want to see how well do the ketones actually circulate throughout the body. And as expected, we actually see an increase in the ketone blood concentration in both of the cells. And so let's look at the tumor metastasis. So for the 41 cells, since they were injected right underneath the skin, we can measure the tumor growth using calipers, basically allowing us to look at the length and the width. And so we plotted that over time, and as time went on, we actually saw a decrease in the tumor area over time. Afterwards, we looked at the bioluminescent imaging, and we simply saw a trending decrease. For the tumor rates and tumor burdens, we actually saw a decrease in tumor rates, we saw a decrease in lung metastasis, and we saw a decrease in spleen rates, all the while maintaining the calf muscle rates. We saw a similar thing for the ranker. We still saw a decrease in the tumor rates, the spleen rates, metastasis, again, all the while maintaining the calf muscle rates. And so that's really good. But afterwards, we want to look at it at a more microscopic level, at a genetic level. And so we performed something called nanostring analysis. And so for those of you guys out in the audience who aren't familiar with this kind of plot, this is known as a volcano plot. And so anything to the left is downregulated. Anything to the right is upregulated. And so we have a line of significance right there. And so that means P is equal to 0.05. So anything below that is not of significance, but anything above it is of significance. And so what we see over here, we see a downregulation of those genes right there. And those genes are actually correlated to those signaling pathways. And the fact that we see a downregulation means that those signaling pathways, which are known to promote tumor growth, would not promote tumor growth in this instance. And then for the ranker cells, we actually see mixed results. So the fact that we see upregulation or downregulation of the AKT signaling, epigenetic regulation, or the DNA damage repair, that's not so good for a study. But we still see a decrease in the hypoxia, which is good. And so afterwards, here are conclusions. Basically, we found that the ketone esters can limit tumor progression and tumor burden. Most importantly, it's a post hypothesis that it can do all of this while maintaining the muscle mass. In the future, we basically want to confirm what we saw on a nanostring level, but now on a protein level. We also want to run additional samples using lung samples, and we want to look at it as a combinatorial agent in humans, maybe using someone like Rishi's doxorubicin. And so I would like to acknowledge these people, Ms. Hong Sin Chen, Dr. Lisa Norian, Dr. Eric Plaisance, and all my friends and family. I'm really grateful for all of you guys. Thank you.
Hello. Hello everyone, my name is Deepak Satish Kumar, and today I'll be discussing my project, exploring T-cell aging across multiple tissues in mice. As people get older, they're more likely to develop chronic inflammatory diseases such as COVID-19, cardiovascular diseases, cancers, and even Alzheimer's disease. It has been previously suggested that the immune system, more specifically T cells, may play a role in this development. T cells are a subdivision of white blood cells that directly attack and kill infected cells. In order to investigate this, mice are typically used, as many age-related changes that occur in humans also occur in mice. Research around the bodies of young and aged mice have been previously conducted and analyzed separately. However, a compilation of single-cell RNA sequencing data from various tissues around the body of mice may yield significant results that would be rather unclear if they were analyzed separately. Single-cell RNA sequencing is a technology that examines and analyzes the RNA transcripts within individual cells, also known as transcriptomes. From a single-cell RNA sequencing dataset, a UMAP graph can be generated as seen in image 2. On a UMAP graph, each data point represents a cell, and similar cells are placed closer together, creating these clusters. Cells that are of the same cluster can be assumed to be of the same type of cell. So the objective for my research was to combine single-cell RNA sequencing datasets and determine any significant differences in their population or their transcriptome in young versus aged mice, and I hypothesized that there would in fact be a significant difference in both population and transcriptome. Here's the methodology I used in my project. First is dataset integration. I sourced 3 publicly available single-cell RNA sequencing datasets that contain cells from all over the body of both aged mice and young mice. This included the liver, the lungs, the heart, etc. Then, using the programming language R as well as the Seurat package, I was able to combine, integrate, and control for batch effects within these 3 datasets. Next is cluster classification. I uploaded my combined dataset into bBrowser X, which is a single-cell RNA sequencing analysis tool. Within bbrowser X, I was able to create my initial UMAP graph, and I performed Louvain clustering, which essentially distinguishes the clusters within a UMAP graph. I was then able to identify each of the clusters that were identified and by their genes that were significantly upregulated or downregulated within those clusters. I then ran another Louvain clustering to get more specific identifications for the T cells in particular. Lastly, using extended functions on bbrowser X and ShinyGo, I was able to produce visual representations of my data that were based on the number of T cells, the age and tissue of the mice, and any significant features of their transcriptome. Here are my preliminary results. Both of these figures are the UMAPs that I generated. Towards the left is my initial UMAP, which contains about 91,000 cells, and towards the right is my T cell subclustered UMAP graph. Both of the respective identifications for those UMAP graphs are listed to the right of each figure. Based on figure 2, I was able to generate figure 3, which shows the absolute number of each T cell cluster within each age and tissue group. As you can see, there's a lot more T cells, immune cells, in the lymph nodes when compared to the heart. This is reasonable as the lymph node serves as the hub of the immune system, and there's a much greater chance of immune cells being present there, while in a healthy heart, there's not much chance for there to be immune cells. One significant finding from this figure was that there was one particular cytotoxic CD8 T cell that increased in all tissues when compared from young to aged mice, as seen in figure 4. This particular cluster was identified for its unique expression of the GZMK gene, and I decided to look deeper into this particular cluster. Table 1 shows the number of each of the T cell clusters that I identified in each age and tissue group. I then performed a two-way ANOVA test to determine if the difference between young and aged mice was in fact statistically significant, and with the p-value of 0.010638, I found that it was in fact significant. I then wanted to assess the role of this particular cell cluster in homeostatic T cell sites, such as the spleen, the peritoneum, and the lymph nodes, to more disease-associated sites, such as the heart, the atherosclerotic plaque, and the liver. And I decided to run a differential gene expression analysis, and the results are shown in figure 6, which is a volcano plot. On a volcano plot, each little dot represents a gene, and the more significantly expressed that gene is, the farther away it is from the origin of the graph. From figure 6, I was able to compile a list of genes that were significantly expressed within this particular cell cluster, and I ran this through ShinyGo, which was that gene ontology analysis tool that I mentioned earlier. What ShinyGo essentially does is, given a list of related genes, it returns a list of biological pathways in which that particular cell cluster may be involved in. The top 5 pathways returned by ShinyGo were mRNA metabolic processes, lymphocyte activation, RNA processing, leukocyte activation, and hemopoiesis, which is the production of lymphocytes and leukocytes. So as you can see, there's a lot of production of white blood cells, there's a lot of activation of white blood cells, and there's a lot of processing going on. Which led me to my conclusion. My data suggests that the cells in this particular cluster increase all over the body as mice age, and additionally, the cells are more activated, cytotoxic, and inflammatory in disease-associated tissues when compared to homeostatic tissues. And we believe that this may point to a possible mechanism of how this particular cell cluster is enhancing disease within the context of aging. In the future, I would like to further investigate the GZMK gene as well as any GZMK-expressing T cell clusters. Additionally, I would like to further investigate other clusters that exhibit significant differences in their population when compared from young to aged mice, as this may provide more insight to the development of chronic inflammatory diseases. I would like to thank the following people for their involvement and encouragement throughout my project, and here are my references. Thank you so much.
Everybody, can you guys hear me? So, hello, my name is Abhay Anand,
and my project title is Parametric Design Optimization of Soft Pneumatic Network Actuators for Rehabilitation. So first of all, what exactly is an actuator? Well, an actuator is a component of a device or mechanism that usually converts pneumatic, hydraulic, or electrical energy into mechanical force or motion. A soft pneumatic network actuator is just a regular actuator that is composed of a silicone rubber structure with a network of inner cavities. Now, this silicone rubber structure makes SPNAs, or soft pneumatic network actuators, cheaper and more flexible than regular rigid actuators. And this is especially important for hand rehabilitation gloves because they can also create a bend when air is inserted into them. Now, while SPNAs might be cheaper and more flexible than regular rigid actuators, they do have certain problems. The biggest issue that SPNAs face is within their structure, and small defects or imperfections within the SPNA structure can magnify and create tears. And so the question that guided my research was, how can I prevent this? And one way to prevent this is to reduce the air pressure needed for SPNAs to curve or bend. And the way I went about this problem was by changing the inner cavity design of the SPNAs to include sloping sides. So as you can see in this trapezoid shape and this triangle shape, if the side is pointing in the direction of tension, which is indicated by the arrows, it is more likely to deform with less pressure. So for that reason, my engineering goal was to design, fabricate, and test SPNAs composed of a network of rectangular cavities, trapezoidal cavities, and triangular cavities. Here are the materials I used. So my methodology included three main parts: the design, the fabrication, and the testing of the SPNAs. So I designed the SPNA molds using a software called SolidWorks. Then after I designed my molds, I then 3D printed the molds. And once the molds were 3D printed, the fabrication process could begin. So first, a Dragon Skin 30 solution was mixed in a centrifuge, and then poured into each of the SPNA molds. The SPNA molds were then placed inside a vacuum for 3 to 4 minutes to remove any air, and then they were left to sit for 24 hours so the SPNAs could cure. And this was for the top part. The base had a similar process, except after the vacuuming, a piece of paper was added on top of the Dragon Skin solution. And after both the base and the top cured, they were combined using a solution Dragon Skin 30. Of course, issues with fabrication did occur. Mainly, I had great difficulty removing the SPNAs from the mold, which caused tears to form. And of course, sometimes air still remained inside the SPNA mold, causing little holes or bubbles to form. So to fix these problems, I implemented new procedures and designs. Mainly, I used mold release to make it easier to remove the SPNA from the mold. And I also changed the design of the triangular mold so that the gaps were larger and air could more easily escape the mold. Here are my finished SPNAs. Okay, so for data collection, I tested each SPNA from pressures between 15 to 75 kilopascals, and for each 10 kilopascal increment, I took one picture. And this picture was later analyzed using a software called ImageJ, which calculated the curvature for these SPNAs. Once the curvature was calculated, I could then find the average radius of deformation, which is just the radius of the circle that best fits the deformation of the SPNA. Using the formula, radius of deformation is equal to 1 over curvature. And then I took this data, and here we can see the basic deformation. So as more pressure is inserted, the SPNA deforms more. So I took the data and, First, let's look at these gloves. So after I tested the gloves, tested the SPNAs, I built 3 rehabilitation gloves. And now finally, after I got the data, I was able to graph it. And we see that between 15 to 55 kilopascals, there's no consistency between the SPNA types. But after 55 kilopascals, we see that the triangular SPNA performs better, meaning it has a smaller radius of deformation than the other SPNAs. And then the trapezoidal SPNA does the same after 65 kilopascals. So what can we conclude from these results? And did I meet my engineering goals? So I did meet many of my engineering goals. I was able to test, fabricate, and design my SPNAs. I was also able to create 3 rehabilitation gloves. And the main thing that we can see from my results is that although there are significant differences between each SPNA, these differences do not indicate that one SPNA performed consistently better than the other at lower pressures. However, at higher pressures, the triangular SPNA and the trapezoidal SPNA perform better than the commonly used rectangular SPNA. So essentially, my molds were able to show improvement at higher pressures. And this is important because rather than going to 75 kilopascals on the rectangular SPNA, we can achieve the same amount of bending or curvature at 65 kilopascals with the triangular SPNA, which reduces the pressure needed and reduces the chance that the SPNA tears. And future areas of research that I can look into are looking at the effect that SPNA cavity shape has on bending force. Bending force is another important aspect of rehabilitation gloves. And also changing other aspects of the SPNA to optimize their performance. For example, the strain limiting layer, the base mold, or even the width of the cavity shapes. I would like to acknowledge the following people for their help and contribution towards my research. Dr. Patibala, who is my mentor, Mr. David Kwong, who is my faculty advisor, and Ms. Shin, who is my research advisor. Here are my references, and thank you so much.
Can you hear me? Hello, my name is Devnos Halley, and I will be discussing my project titled The Exploration of the Utility of Genotyping and Whole Genome Data from the Alabama Health Initiative. Current electronic health records are not the most efficient way of storing patients' medical information. This is due to the sheer amount of information that healthcare workers have to manually input into these EHRs themselves. A study done by the Annals of Internal Medicine has shown that most U.S. institutions have to manually input, on average, 4,000 characters, or approximately 800 words themselves. The Annals Internal Medicine also found that, on average, healthcare workers spend approximately 16 minutes and 14 seconds, or 974 seconds, mainly inputting patients' medical information to EHRs. This utility amount of information often leads to professional burnout. This professional burnout could lead to impacted work efficiency, or could even lead to resignation from their jobs. And this leads to my engineering question. The creation of a program that uses a patient's genetic mutations to provide what certain symptoms/conditions they may face due to that mutation. This is to lessen the workload for those healthcare workers, also to find a more time-efficient way to document their information. These information were used in this research. This is the overall methodology, and I will be going over the database creation, filtration, the downloaded needed information, the matched genetic information input, and the genuine output from the program. Starting off with the database creation, what I did is that I used the ACMG genetic list of recommendations of genetic diseases. Each genetic disease has a corresponding gene, and each gene has a corresponding ClinVar link, which links to a table list that has variants of that gene that the ACMG found to be of clinical significance that caused the genetic disease. What I then did was download each ClinVar table as a text file and upload that into DB Browser for SQLite. However, some of the variants in this database had IDs called DBSNP IDs that had value of null. Without the DBSNPs, my program wouldn't be able to actually identify those variants. So what I had to do was filter those out using execute SQL, which led to this database, which would be actually used in this study. The actual genetic input consisted of a long text file with a patient's genetic variations that matched to see if there was a match in this database here. If a match was found, it would use the list of diseases here in the following ChatGPT search query. List what symptoms I will face given that I have the following diseases, plus the diseases listed here. Then the DBSNP ID, the diseases, the ACMG variation link, and the result of that search query would be added to a list, which would be outputted at the end of the program, which would also output how long the program ran for. These are the actual results of the program with all the variants that the program found, along with the actual ChatGPT search query result, which is what would actually be documented to an electronic health record. Additionally, if you remember, as I stated in the beginning, healthcare workers on average spend approximately 974 seconds documenting each patient's EHR. However, from 10 sample runs, you can see that my program did it in only 109.272 seconds. The program was successfully able to list the conditions that the patient may undergo given their genetic mutations. Also, as I stated before, the average runtime from 10 sample trials was 109.272 seconds. However, due to the fact that the ACMG didn't provide conditions listed for the RS1137617 variant, the program was unable to give like a genuine query for that specific variant. While this method of writing EHR is time-wise more efficient, it's important to note that just because a patient has the mutation doesn't mean they'll actually experience the symptoms that were returned. Two patients can have the same mutation, however, one patient can have severe symptoms while the other has none. Additionally, these queries should be interpreted cautiously by healthcare workers, as AI, especially ChatGPT version 3.5, has a tendency to lie and provide misinformation. In the future, I would like to use actual patients to actually verify that they would experience the symptoms that ChatGPT had returned. Additionally, use other AI models that are smarter than version 3.5, such as ChatGPT version 4.0. I would like to acknowledge my mentor, Dr. Shamina at UAB, my faculty advisor, Ms. Templin, Dr. Flournoy, the head of the math science faculty, Ms. Chen, my friends and family. These are my citations, and thank you for your time.
Yes. So, we have a second before the reception. All the seniors, I'd like you guys to come on stage so we can take some pictures of them. So all the seniors. And also be recognized. Also, if any of you have any questions for them, now is a good time to ask them any questions about their research. It's a perfect time. But also, like I said, I'd like you guys to congratulate them on their job well done today. They worked really hard. Is there anybody? David, can you take a picture? That's a good question. There's a lot of
I'm going to do the mom thing.
I guess you guys are just looking all over the place. It's my fault.
Wait. That's a good one.
Finally, closer.
Oh, Dr.
I had a really comfy chair. Like, it'll make me move. You got it already? Thank you so much. All right, we're good. I moved for no reason.
Okay, stay there. Wait. Stay there.
More pictures.
Couple more.
All right, stay there. Smile. Smile really big.
Does anybody have any questions for any of the students? How does it feel to be finished?